Enthalpy is a measurement or quantification of heat flow that's occurring in a system for a specific process. And this process is actually occurring at constant pressure. So because of this, we have the relation of energy flow and, of course, pressure and volume changes. So enthalpy can be represented by this H equals E plus P times V. And we can go ahead and look at how the relationship of enthalpy to pressure volume work allows us to get this type of equation. Now remember, energy, pressure, volume, these are all state functions, so enthalpy by default is also going to be a state function. So we're going to go ahead and look at how heat flow and enthalpy are directly related with a little mathematical representation. So remember, pressure volume work, we know that at constant pressure, work is equal to the negative P delta V. We saw that in our previous lecture set. And we can utilize this equation in order to show the relationship between enthalpy and heat. Okay, so remember that internal energy, the change in internal energy, is equal to the sum of our heat and our work values. So taking this equation and substituting in our work equation, okay, we get the equation delta E equals Q minus P delta V. And then if we look at this equation and rearrange to solve for Q, we're going to end up with Q being equal to delta E plus P delta V. And that's what we get right here. So utilizing the pressure volume work equation, that W equals negative P delta V, and plugging it into the internal energy equation, we can get the relationship between our heat value, our Q value, our change in energy, and our work associated with pressure volume work changes. Now we know that our enthalpy equation relates our enthalpy value with energy and pressure volume work. So we could very much easily manipulate this equation to look at the changes in enthalpy and their relationships to the change in energy and the change in pressure volume work as well. What I want you to notice is that both Q and delta H are equal to the same variables. So Q is equal to delta E plus P delta V, and delta H is equal to delta E plus P delta V. So both delta H and both delta H and Q are actually equal to the same things based on the utilization of the pressure volume work equation. So what we understand there, what we can infer from there, is that delta H, our change in enthalpy, is going to be equal to Q. So enthalpy is equal to the heat flow into or out of the system, and basically enthalpy allows us to measure this heat flow. Now, this relationship here is one of the reasons why heat of reaction and enthalpy changes are interchangeable with systems that are occurring at constant pressure. So enthalpy and heat flow can sometimes be somewhat interchanged, but please realize that they are separate. Remember, enthalpy is a state function, heat flow is not. But the tracking of them is very similar because of the fact that at constant pressure, the change in the enthalpy of a system is going to be measured or followed by the energy flow that's occurring as heat. So just make sure that you're differentiating between what each piece means, so enthalpy versus heat flow, but also understand how they're related and under what conditions they're related. So enthalpy changes for chemical reactions are going to be looked at with respect to this equation. So your change in enthalpy is going to be equal to the enthalpy of your products minus the enthalpy of your reactants. We'll be using this type of equation to figure out the enthalpy of specific reaction types, and we'll talk about that in a little bit. But before we get to those types of calculations, I want to understand what this calculation will tell us. So when we end up with products that have a greater enthalpy value than reactants, the delta H that we solve for is going to be positive. Okay, in the reverse thought, if the reactants are greater in enthalpy than the products, we'll end up with a delta H that is negative. So these two features, or these two delta H values, can be utilized to decide if we have an exothermic or endothermic reaction. If delta H is negative, we have an exothermic reaction, and if delta H is positive, we have an endothermic reaction. And the reason why we can make this correlation with the exothermic or endothermic properties of a reaction and delta H is that most reactions are occurring under constant pressure conditions. So you have containers that are open, such as test tubes and stuff like that, or that a reaction is taking place in a system that basically allows that pressure to remain constant. Also, usually there's very little work associated with any changes of products, so you don't have to worry about that pressure volume work aspect. So this correlation of delta H values and the exothermic or endothermic properties of the reaction works for the majority of times that you're doing reactions in chemistry. Now, enthalpy of reactions, or delta H of Rxn, as you see here, are basically enthalpy changes that are accompanying a specific reaction type. We're still going to be using this equation that we talked about. So delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. In this case, we're going to be looking at it with respect to a specific reaction. Now, enthalpy of reactions are going to be represented by thermochemical equations. So what are thermochemical equations? Basically, they're balanced equations that show the specific enthalpy change for the specific molar amounts in that equation. So what do I mean by that? Okay, well, I mean that I have a change in enthalpy value associated with the reaction that's been given. So right here, I've been told that I have an enthalpy value of negative 890.4 kilojoules. So what this value means is that negative 890.4 kilojoules of enthalpy are going to be released, and I know it's released because we have a negative sign here, for every 1 mole of CH4. Okay, so the molar quantities in our reactants and from our equation are going to directly dictate how that relationship is between enthalpy and the amount of substance. So what that would mean is that for every 1 mole of CH4 that I burn in the presence of O2, I'm going to get negative 890.4 kilojoules of enthalpy. So basically, the big feature here, the big thing for you to take away is that this thermochemical equation and this enthalpy value are directly related. Changing this thermochemical equation, any of its coefficients or anything of that sort, would subsequently change your enthalpy value. Also, changing any of your states of matter, that could change your delta H, and we'll talk about that more specifically later. So enthalpy of reaction is for a very specific reaction set. It's not just a generic term, but we're going to treat it very similarly because we're utilizing this equation that we talked about on the previous slide. So let's go ahead and put the use of our thermochemical equation and our enthalpy value associated with it into practice for solving actual problems. So they ask us here, how much heat is evolved when 266 grams of white phosphorus, which is represented as P4, burn in air. So they've given us a thermochemical equation. Notice that the white phosphorus is burning in the presence of oxygen to give us P4O10. And they've given us an enthalpy value associated with that. So if I look at my balanced equation and my enthalpy value, I can establish the relationship between enthalpy and P4, because that's the substance they're asking about. So I know that I have 1 mole of P4 for the release of this enthalpy. So I have negative 3013 kilojoules for every 1 mole of P4. So this is my conversion factor. Now, they gave us or they asked this question with respect to 266 grams of white phosphorus. So really, I know how many grams of this white phosphorus I have, but the conversion factor is not with respect to grams of P4, it's with respect to moles of P4. So I need to make those units match. So in order to go from grams of white phosphorus to moles of white phosphorus, I'm going to divide by the molar mass. So that's what I've done here. So that's my first step. Okay, and then in order to go from moles of P4 into kilojoules of P4, I'm going to use the conversion factor that I established from the thermochemical equation, which is this one right here. So 266 grams of P4 times 1 mole divided by 123.9 grams of P4 times 3013 kilojoules divided by 1 mole of P4. Okay, that's going to give me 6,470. Now, if I do a unit evaluation, grams of P4 and grams of P4 cancel, moles of P4 and moles of P4 cancel, and kilojoules are what we have left over. So, when I have 266 grams of white phosphorus and burn it in the presence of air, according to this thermochemical equation, 6,470 kilojoules of heat are going to be involved. Now remember, delta H and Q are directly related to each other. We saw that a few slides back. So this relationship in terms of having an enthalpy value but them asking about heat is completely plausible and acceptable. So make sure in this type of problem that you're figuring out the conversion factor based on the molar amounts of your coefficients on your chemical equation, as well as the enthalpy value. Once you get that, then take the item that you've been given, so in this case we were given white phosphorus, and make sure that it's in the appropriate units in order to be converted into the kilojoule value or the joule value, whatever your units are in. So, so the problem that they've given us here is when 1 mole of methane is burned at constant pressure, 890 kilojoules of energy is released as heat. Calculate delta H for a process in which a 5.8 gram sample of methane is burned at a constant pressure. Okay, so guys, remember that, delta H is equal to Q at constant pressure systems. So we can use the interrelationship between Q and H to figure out or to solve for H. So let's first of all look at what they have given us. They told us that 1 mole of methane is burned at constant pressure and that 890 kilojoules is released from the burning of that 1 mole of methane. So when it says energy is released as heat, we know that our Q value is equal to negative 890 kilojoules. Why do we know that? We know that it's negative because the heat is being released. It's exothermic. So Q is leaving the system. Heat is leaving the system. And we know that because we burned exactly 1 mole in order to get that quantity of heat, we know that the relationship between our heat and our amount of burned methane is as follows. So basically, for every 1 mole of CH4, 890 kilojoules of heat are going to be released. So now that we have this relationship, we need to figure out how much of this heat is actually going to be released when all we're burning is 5.8 grams of methane. So basically, they've given us the information to establish our conversion factor. They've given us an information to understand that delta H and Q are equal. We understand that. They've given us the information we need to understand that heat is being released, so that our Q value is going to be established as negative. So they've given us a bunch of information. So now we can treat this very much like the previous question because we have both our conversion factor and our quantity of material we were given. So we have 5.8 grams of CH4, okay, So we need to go from grams of CH4 into moles, because our conversion factor here between our heat and our moles of reactant by default make us need to be into moles. So in order to go from grams of CH4 to moles of CH4, we need to divide by the molar mass of CH4, which is 16.0 grams for every 1 mole of CH4. Okay, so now that we have that established, now we can go ahead and plug in our conversion factor down here, because we'll be in moles of CH4, so I can plug in 890 kilojoules for every 1 mole of CH4. So we go ahead and we multiply everything across the top, divide by everything that's on the bottom, and that's going to give us negative 320 in terms of our numerical value. If we go ahead and do a unit evaluation, grams of CH4 cancel, moles of CH4 cancel, and kilojoules is what we have left. So our answer will be kilojoules. So because this is our heat value that's been released, but we know that delta H and Q are equal, so delta H is going to be equal to negative 320 kilojoules. Okay. Once again, make sure that you're paying attention to your units, what they've given you. Make sure that you establish the conversion factor based on what you've been given. And make sure you're paying attention to signs and things of that sort. Okay, energy being released and energy flow are going to help you establish and dictate that sign of that heat flow or energy or any other substance. So make sure you're paying attention to those types of things. So now that we've looked at enthalpy of reactions with respect to thermochemical equations, there's a few other things that we need to actually understand about thermochemical equations. So basically, if we look at this reaction here, notice we're combining H2 and O2 to give us H2O, and that gives us a specific enthalpy value. So for every 2 moles of H2 that are combined with oxygen gas, we get negative 483.6 kilojoules of enthalpy. So that at constant pressure, that heat release is directly related to those molar amounts. Now, remember, delta H of reaction is proportional to the marine amounts of reactants that are present. So we look at this equation, and we have this enthalpy value being released. Now, if we look at this equation here, what you should notice is that the coefficients are different. It's the exact same reaction, but the coefficients are larger. Everything's been multiplied through by 2. So we should expect a change in the overall enthalpy value, right? Okay, so notice it has doubled when we've gone from only 2 moles of H2 to 4 moles of H2 in this exact same reaction. We would expect a doubling of the enthalpy released. So that should make intrinsic sense. You have more substance, so you should theoretically have, you have twice the substance, so you should have twice the amount of energy being released, twice the amount of heat being released. Delta H of reaction is going to be, or have the same magnitude, but a different sign if the reaction that you're looking at is the reverse. So notice this first reaction right here, it's an exothermic reaction. But if we flip that reaction, basically we split the water, we actually end up with the same numerical value, but a new sign. Okay, the sign has to be flipped because it's the reverse process. So if the forward process, the regular process, releases energy, the opposite of that, the reverse process, must absorb energy or must absorb heat in order to occur. So please make sure that you're comfortable with these two concepts. Now, delta H of reaction also depends on the states of the reactants and the products. And this concept is going to become extremely important when we're doing Hess's law calculations, which will be looked at in our next presentation. So remember, enthalpy basically is a measurement that allows us to quantify heat flow. At constant pressure situations, you're going to be able to relate your delta H of your specific reaction to your heat flow to Q. and that kind of leads to somewhat interchangeable features. Please understand that they are different ideas, or they are different representations, but they are connected in a very unique and helpful way.